Your coolant is probably failing right now, and it still looks perfect. Not because it's leaking, not because it turned rust brown in the reservoir. It's still that clean green or orange color. Maybe you had it flushed 18 months ago. Maybe there's a sticker on your hood that says, "Good until 30,000 miles," and you've got 28,000 on the clock. Here's what that sticker doesn't tell you. By the time coolant looks bad, it's been doing damage for months. Corrosion starts at the molecular level on aluminum heads, on the water pump housing, on the inside of the radiator, long before your eyes can see anything wrong. The color doesn't tell you if the chemistry is still working. And it's the chemistry that's actually protecting your engine. Japanese automakers figured this out a long time ago. Starting in the 1990s, Toyota, Honda, Mazda, and Subaru moved to a fundamentally different type of coolant chemistry. The result? Coolants that are rated to last 100,000 miles instead of 30,000. Not a marketing number, a reflection of the underlying chemistry. And there's a class of additive, cheap, available, and used in virtually every long-life Japanese OEM coolant that you can buy for a couple dollars. Understanding what it does, whether it actually works, and why most shops never bring it up, that's what this video is about. Cooling system failures are one of those slow disasters that look cheap to prevent and expensive to ignore. A coolant flush, $100 to $200 at most shops. Fine. But what actually happens when coolant chemistry fails a warped cylinder head, a blown head gasket, aluminum corrosion eating your water pump? Those repairs run $1,500 to $4,000, sometimes more. And they don't come with a warning light. They come with a temperature gauge that suddenly goes wrong on the highway. The average American drives a car for more than a decade. Over that span, the cooling system operates in brutal conditions. Sub-zero winters, 220-degree engine heat,
constant pressure cycling, and a mix of dissimilar metals. Aluminium heads, iron blocks, copper radiator cores, brass fittings, all in contact with the same liquid. Every one of those metal-to-liquid interfaces is a potential corrosion site. Here's the question this video answers. Is there a chemically sound, legitimate way to extend your coolant's protective life beyond what most shops recommend? And does a cheap Japanese-style additive actually accomplish that? Short answer, yes, with conditions. The conditions matter, and most videos skip them. This one won't. Most people think coolant is simple. You mix antifreeze with water. You get freeze protection and heat transfer. Flush it every couple years. Move on. That's not wrong. It's just incomplete. And the part that's missing is the part that actually saves your engine. The active ingredient in antifreeze is ethylene glycol. That's what lowers the freezing point and raises the boiling point of the coolant mixture. But ethylene glycol, by itself, is mildly corrosive. Left alone, it would eat the aluminium and iron in your engine. What keeps that from happening is the corrosion inhibitor package. It's a blend of chemical compounds mixed into the coolant at the factory. These inhibitors coat metal surfaces with a microscopic protective film, buffer the pH so the fluid stays neutral instead of acidic, and prevent a specific type of damage called cavitation erosion on the water pump impeller. The inhibitor package is the engine's real chemical defense. And here's the critical thing. Those inhibitors deplete. Every heat cycle, every mile, every interaction with bare metal uses up a little of that protection. The ethylene glycol stays stable for a long time. The inhibitors don't. Eventually, they're gone, and bare metal is being slowly exposed to hot, pressurized, slightly acidic fluid. That's why coolant has a service interval. Not because the glycol breaks down fast.
The interval exists because the inhibitors run out. Now, different inhibitor chemistries run out at very different rates. The conventional green coolant most Americans grew up with uses what's called IAT chemistry, inorganic additive technology. The inhibitors are silicates and phosphates. They work fast and form a protective film quickly. They're also well understood and forgiving of contamination. But they deplete in roughly 2 years or 30,000 miles. That's where the flush it every 2 years rule came from. That rule was literally built around IAT's depletion timeline. Japanese automakers started moving away from IAT in the 1990s. They shifted to OAT, organic acid technology. Instead of silicates and phosphates, OAT coolants use carboxylate compounds, organic acids that form a thinner, more targeted protective film. They react selectively, binding only where corrosion is actually beginning, rather than blanketing every surface indiscriminately. The payoff is longevity. OAT inhibitors are far more chemically stable. Toyota's super long-life coolant, OAT-based, specified for most Toyotas since the early 2000s, carries a first change interval of 100,000 miles or 10 years. Honda's Type 2 coolant carries similar specs. That's not marketing. That's OAT chemistry doing what IAT never could. Here's what this means for you. If your car is a Toyota, Honda, Mazda, or Subaru from the last 15 to 20 years, and your shop is recommending a coolant flush every 2 years, they are either applying IAT logic to an OAT system, or they know the difference and they're banking on you not knowing it. So where does the cheap Japanese additive come in? OAT coolant lasts longer than IAT, but it still fails eventually. The organic acid inhibitors still deplete. They bind to metal surfaces, they get consumed, and the pH still gradually drops. The coolant can look fine while its protective capacity is fading.
Here's the question Japanese automotive chemists have been working with for decades. What if you could replenish the inhibitor before it's fully gone? This isn't a fringe idea. It's actually standard practice in heavy-duty diesel engine maintenance. Fleet operators, trucking companies, construction equipment, agriculture have used something called supplemental coolant additives, or SCAs, for decades. These are concentrated corrosion inhibitor packages you add to the cooling system on a schedule, refreshing the protection between full fluid changes. The practice is documented in service guidelines from Cummins, Detroit Diesel, and Caterpillar. It's not a YouTube hack, it's industrial maintenance. For gasoline passenger cars, the equivalent is less standardized, but it exists, and it's most developed in Japan. Japanese auto stores, Autobacks, Yellow Hat, Pitwork, carry a category of product that barely has shelf space in the US: cooling system conditioners. Small bottles, inexpensive, specifically formulated to add fresh OAT-compatible corrosion inhibitor to aging coolant. Brands like Waco's, a Japanese chemical company with genuine OEM credibility. Their products are used in racing applications and have a serious following in the JDM enthusiast community. Make coolant treatment products built on legitimate organic acid inhibitor chemistry. Idemitsu, one of Japan's major petroleum companies and an OEM fluid supplier to multiple automakers, offers similar products. The active chemistry in a quality OAT conditioner, typically a carboxylate blend, sometimes with molybdate for copper and brass protection, sometimes with toluyltriazole to prevent galvanic corrosion, directly addresses the mechanism by which coolant protection fails. This isn't marketing language. These are the same compound families specified in ASTM International Coolant Standards. The $2 price point in the title? In Japan, these products are genuinely cheap and mainstream. In the US, OAT-compatible conditioners exist, but are harder to find and less visible on store shelves. The market hasn't caught up to the chemistry. Now, let's address the two biggest claims directly. Forever. No, that's not physically possible, and anyone telling you otherwise is selling something harder than I'm willing to sell. Inhibitors deplete. Glycol degrades at extreme mileage. Contaminants accumulate. There is no additive in existence that renders coolant permanently protective. What the title is clumsily pointing toward, and what's actually supportable, is the idea that periodic, small additions of fresh OAT inhibitor can meaningfully stretch the interval between full coolant changes. Whether that appeals to you depends on whether you're the kind of person who'd rather manage your chemistry than pay for a flush on the shop's schedule. Repair shops want this banned. Shops don't want anything banned. That framing is conspiratorial nonsense. But there is something real underneath it, and it deserves a straight explanation. A coolant flush is a profitable, low-complexity service that's easy to bundle with an oil change. If the coolant in your car is rated for 100,000 miles, and you understand enough to check your pH and add a $5 conditioner when the numbers drop, that flush doesn't sell itself. There's no dark conspiracy. It's just that the shop's recommended service interval is often a default number, not a vehicle-specific one, and the default tends to favor the shop's revenue more than your OEM specification. That's the real incentive misalignment, not a cover-up, just a business model that benefits from you not knowing your own coolant spec. Here's what's verifiable. Toyota's super long-life coolant specification and the 100,000-mile first change interval is documented in Toyota owners' manuals and dealer service publications. It's OEM specified, not an aftermarket claim. A shop recommending a 30,000-mile flush on a Toyota running SLLC is recommending a service the OEM does not require at that interval. Honda Type 2 coolant carries equivalent extended interval specs. Mazda's FL22 coolant, a specific formulation used in many Mazda models, is rated for approximately 75,000 miles. These are engineering specifications, not marketing positions. The mechanism of corrosion inhibitor depletion as the primary coolant failure mode is reflected in ASTM international standards for coolant testing. ASTM D1287 covers pH measurement. The D3306 and D6210 specification families define performance requirements for coolant, and the test methods within them focus heavily on inhibitor reserve and metal corrosion protection. These standards exist precisely because inhibitor chemistry, not glycol chemistry, is the critical variable. The use of supplemental coolant additives in heavy-duty diesel applications is documented in Cummins service publications. Cummins specifies SCA concentration ranges, testing intervals, and top-up procedures. The principle that periodic inhibitor replenishment extends cooling system protection between full fluid changes is not hypothetical in that application. It's standard fleet practice. What the evidence doesn't give us, and this is worth being direct about, is a clean, published, peer-reviewed study on cheap OAT conditioner additives in consumer gasoline engines. The heavy-duty diesel SCA literature supports the mechanism. Forum-based long-term reports from enthusiast communities are consistently positive, but aren't controlled testing. The chemistry is sound. The specific consumer application evidence is thinner than I'd like. Know that going in. Here's what you can actually do. Step 1. Find out what coolant is in your car. Pull the owner's manual and look for the coolant specification. It will reference OAT, HOAT, or a brand name like SLLC, Type 2, FL22, or Dex Cool. If your shop is recommending a 2-year flush and your manual specifies a long-life OAT coolant, ask them to show you where that interval comes from.
If they can't answer that, or if they plan to refill an OAT system with generic green IAT antifreeze,
that's a red flag. Step 2. Test your coolant's actual chemistry. Coolant test strips are available at any auto parts store for under $10. They measure pH and freeze point. A healthy OAT system should read between 7 and 11 on the pH scale. Below 7 means the inhibitors are depleted and the fluid is acidic. Corrosion is already accelerating. If you're there, no additive alone is the answer. You need a flush. Step 3. Use OAT-compatible additives if your coolant is aging but not failed. If pH is dropping but you're not at a full flush interval yet, an OAT-compatible corrosion inhibitor additive is a legitimate option. In the US, look for products that explicitly state OAT compatibility. Do not mix inhibitor types. Adding a silicate-based product to an OAT system or vice versa can cause the inhibitors to chemically react with each other, precipitate out of solution, and stop working entirely. Compatibility matters more than price. Step 4. Don't replace the flush permanently. Additives extend intervals. They don't eliminate them. At high mileage, a complete drain and refill with fresh OEM spec coolant is still the right call. The goal is to flush when the chemistry actually demands it, not because a calendar or a shop's upsell menu says so. Step 5. Ask the right question before approving any service. What coolant specification does my car require, and is that what you'll be refilling it with? That one question separates the shops that are thinking about your car from the ones that are thinking about their throughput. A few honest boundaries on everything above. The value of any coolant conditioner additive depends on how depleted the coolant already is, what type of coolant is in the system, and the specific product used. If your coolant is severely degraded, visible rust, significant pH drop, scaling in the reservoir, an additive won't reverse that. You need a flush first. Modern cooling systems vary significantly by make, model, and year. Aluminum-heavy engines, which is most cars made in the last 20 years, are more sensitive to coolant chemistry errors than older iron block engines. Putting the wrong inhibitor type in the wrong system isn't neutral. It can actively make things worse. And on warranties, adding any aftermarket product to your cooling system is worth a careful read of your warranty terms. In most cases, an OAT-compatible additive in an OAT system won't void coverage for unrelated components. But if a cooling system component fails while there's an aftermarket additive present, a dealership has an easy argument. Understand the trade-off before you open the bottle. Here's the short version. The chemistry is real. Japanese automakers spent decades building OAT coolant technology because organic acid inhibitors are genuinely more stable and longer lasting than the silicate-based chemistry in conventional green antifreeze. The inhibitor package is the engine's actual defense, and inhibitor depletion is the actual failure mode. A quality OAT-compatible corrosion inhibitor additive, whether it comes from Japan, Germany, or your nearest auto parts store, can legitimately extend that protection between full fluid changes. Not forever, meaningfully. The $2 price point is real in Japan. The band framing is not. The chemistry underneath it? Worth knowing. Check your coolant spec. Test your pH. Don't let a shop flush your 100,000-mile OAT coolant at 30,000 miles, because the default service schedule said to. If this changed how you think about your cooling system, pass it to someone who's about to say yes to a flush they probably don't need yet.